your pre-lab, question number 3, you are asked to calculate the molarity of a KOH solution that was used to titrate 0.7038 grams of KHP. In order to answer this question, the first thing you need to do is understand the equation of what's happening in the process. So I've written out a balanced equation. This is KHP reacting with KOH, and it makes K2P and H2O. KHP, just as a side note, is potassium hydrogen phthalate as described in problem number 1 of the pre-lab. The P does not stand for phosphorus, it stands for the phthalate ion. So you can see from this equation that KHP and KOH react with each other in a 1-to-1 ratio from their stoichiometric coefficients, and that's going to be important when we go about and solve the problem. Now what I have here is a problem that's similar to question number 3 in your pre-lab, but it's not exactly the same. It's the same idea. We have 1 gram of KHP and it's titrated with 50 mils of KOH solution. What we want to know is the molarity of the KOH solution. So in order to begin, let's start by thinking about what variables do we need to have in order to determine the molarity of the KOH solution. Molarity is moles divided by liters. So we need to know the moles of KOH and the volume of the KOH solution. The problem tells us our volume. It's 50 milliliters or 0.05 liters. So we've already got that information. We just need to figure out how many moles of KOH we have. And we know from the balanced equation, from the 1-to-1 ratio, that every 1 mole of KHP is equivalent to 1 mole of KOH. So if we figure out how many moles of KHP we have, we will know how many moles of KOH we have. We don't have moles of KHP, but we do have grams. So we can use the molecular weight of KHP, which is 204.2 grams per mole, and we can convert grams into moles of KHP. So for this particular problem, we're going to get 0.0049 moles of KHP, and because of the 1-to-1 ratio, we know that we must have also had 0.0049 moles of KOH in order for these two things to be able to react with each other in a 1-to-1 ratio the way it's described in the equation. So now that we've got that figured out, all that we have to do is plug these numbers into our molarity equation. Remember, it's moles of KOH divided by the volume. So we're going to plug in our 0.0049 moles of KOH and the volume of our solution, 50 milliliters, which is 0.05 liters, and that's it. So there's that. For your lab, in your post-lab, you're going to be doing these calculations as well, although in your lab you're using NaOH instead of KOH. That doesn't change any of the way that you do the calculations. You would just change the K to sodium Na, but nothing else in terms of the way you go about calculating the molarity. Nothing else will change. So in problem number 4 of your pre-lab, you are asked a very similar question. In order to understand this question, which has to do with titrating HCl with KOH, first thing that we want to do is look at the balanced equation. HCl reacts with KOH in a 1-to-1 ratio to make KCl and water. Again, a 1-to-1 ratio between HCl and KOH. This problem is very similar to question 4 of your pre-lab. 25 milliliters of HCl are titrated with 30 mils of 0.1 molar KOH, and we want to know what the molarity of the HCl solution is. Again, the molarity is moles per liter, and just like in the previous problem, we know the volume of the HCl solution, 0.25 milliliters, but we don't know the moles. We do know the relationship between moles of HCl and moles of KOH, and we have the ability to figure out the moles of KOH. If we can calculate the moles of KOH, we will know the moles of HCl. So we are going to use, and this calculation is a little bit different than the one we did for the KHP. In this calculation, we use the molarity of KOH and its volume to get the moles. 0.1 molar KOH, remember, by definition, is 0.1 moles per 1 liter, the definition of molarity. If we multiply this by the volume of KOH, 30 mils, which is 0.03 liters, if we multiply the molarity by the volume, the liters of solution cancel out, we're left with moles of KOH. In this problem, it's 0.003 moles of KOH. Because of the 1-to-1 ratio, 0.003 moles of KOH is exactly how many moles of HCl we have, 0.003. And then again, we're just going to plug that into our molarity calculation. 0.003 moles of HCl divided by the volume of HCl in liters, 0.025, and that is the molarity. And you'll do this, again, you'll do this in your post-lab as well, only in your post-lab you'll be using NaOH instead of KOH. That does not affect the way you calculate it, just the way that you write it down. So in your post-labs, part of what you're doing is just reporting your data, writing it down. You're going to calculate NaOH molarity from volumes or masses of KOH, which will be just like this. And you'll also calculate an HCl molarity from NaOH, which will look just like this. But also in your post-lab, one of the things that you have to do is do a percent error calculation. And so percent error calculations, you're going to, in doing this is going to be how you determine whether or not your titration data is good. You'll start by just doing 3 titrations in a row and calculating the molarities. And I've just come up with some random numbers. I don't know if these are anything like what you'll actually get in the lab. Let's say you do 3 titrations, you have 3 trials, you calculate 3 different molarities from each trial. And what you need to do is calculate the error associated with these 3 trials in order to determine if they are accurate enough. To do this, you're going to find the difference between your biggest and smallest, or highest and lowest molarities. In this, our highest molarity is trial number 2, and our smallest is trial number 3. The difference between them, just from subtraction, is 0.00095. Once you figured out the difference, you're going to then calculate the average of the high and low titration molarities. So there I'm adding them up, dividing by 2, and that's my average molarity. And then you are going to take the difference divided by the average, multiplied by 100 to turn it into a percentage. So my difference, 0.0095, divided by my average, multiplied by 100 is 7.6%. That's too high. The lab procedure tells you what is an acceptable percent difference. It is not 7.6. If your percent difference is too high, you need to do another trial, at least one more. Just do one at a time though. So here we do trial number 4, we get another molarity, and after trial number 4, we're going to recalculate our percent differences using the 3 trials that are closest to each other in molarities. So looking at my 4 trial molarities, I can see that trial number 2 is the biggest. And not just that it's the biggest, but it is the most different from the other 3. 1, 3, and 4 are pretty close to each other in terms of value. So I'm going to recalculate the percent difference only using trials 1, 3, and 4 for my calculations. Find the difference between the high and the low, which is still, oh no, it's different now. Because we've discarded trial number 2, my high is 0.01206, and my low is trial number 3, 0.01198. So there's my difference. And then we calculate their average and do difference divided by average times 100, 0.67%, which is good. If 1% or less is good. So this means that trials 1, 3, and 4 are close enough to each other to be used, and those are the 3 trials that you'll use to calculate the average molarity. You will do the same percent error calculation in the last part of your pre-lab with hydrochloric acid, and in that you'll follow the exact same procedure.